Hi. In this video, we are going to start by looking at the Cauchy's inequality and we are going to apply it to problems. So let's get started. The inequality is stated as follows. Let AI bi belonging to real where I goes from 1 to n. Then we can say that summation of I goes from 1 to n AI bi product whole square is less than equal to summation of I goes from 1 to n ai square multiplied by summation of I goes from 1 to n bi square. So what is this inequality about? You should think of A as a vector with components. So let's say A1 I cap and A2 j cap and so on so on. There are n dimensional vector A and B is another vector with components B1, B2 and so on Bn, right? If you think of these two vectors, the dot product of these two vectors is a1 b1 plus a2 b2 till an bn, which is basically the summation of ai bi, where I goes from 1 to n. And we also have an alternative definition of dot product, which is mod a mod b cos theta. So now, since mod a mod b cos theta must be equal to this ai bi, we know that cos theta is less than equal to 1. Therefore, we can say that summation of ai bi must be less than equal to mod a and mod b, right? Or summation of ai bi whole square must be less than equal to mod a square and mod b square. And how do we write mod a square for a vector? We do summation of ai square multiplied by summation of I, this is bi square. These are the components themselves squared and added. That is the modulus of A vector. And similarly, this is modulus of B vector. So that gives us the Cauchy inequality, right? So obviously that is essential for understanding how it has come about, but we'll be using this inequality directly. So here, when is the left-hand side equal to RHS? When are they equal? That happens when the vectors A and B are parallel to each other, or when every component bi is lambda times ai. For all I goes from 1 to n, lambda is a real number. So when the vectors are parallel to each other, when this is satisfied, you will have equality case in Cauchy's inequality, right? Let's look at some of the applications of this Cauchy. So basically some corollaries for Cauchy's inequality. The first case is n times summation of I goes from 1 to n ai square is greater than equal to summation of I goes from 1 to n ai whole square. What is this? Here we are saying all the bi's are 1. All the bi's are 1. So basically, this is the square of the mod, right? So the mod b vector would be root over n. So mod b square is n. So therefore, this is basically mod a square mod b square is greater than equal to a dot b whole square. A dot b will be simply ai into 1 plus a2 into 1 plus a3 into 1 and so on. So this is simply this. So eventually, like you should learn that to use this directly. We are just applying Cauchy's inequality in the case when all the bi's are 1. We get this. The second corollary that you should be aware of is summation of I goes from 1 to n ai multiplied by summation of I goes from 1 to n 1 by ai. This is greater than equal to summation of I goes from 1 to n ai into 1 by ai whole square, which is equal to n square. So basically this is greater than equal to n square is the corollary, right? So here again, the vectors here are basically, this is the dot product part, this is the modulus part, right? So a1 plus a2 and all, a1 plus a2 plus an This is the modulus of some vector. So basically, this must be, the vector must be root a1, root a2, and so on, root an. This is the a vector, n-dimensional vector. And similarly, the b vector would be 1 by root a1, 1 by root a2, and so on, 1 by root an. So if you apply Cauchy on these two vectors, you will get this result. This is the second result that you should be aware of. The third one is this one, where we say summation of ai bi multiplied by summation of ai by bi is greater than equal to summation of root ai bi into root ai by root bi whole square. And so this bi gets cancelled, and this is equal to summation of ai whole square. So again, this is Cauchy, and the vectors are a little more complicated, but this kind of thing happens many times in problems. So you should be aware of this result. And the last corollary that you should see is this one, summation of bi multiplied by summation of ai square by bi is greater than equal to summation of I goes from 1 to n. This time it will be root bi into ai by bi. So it will be ai whole square. Again, apply Cauchy to the vectors root bi. The vector b is root b1, root b2, and so on, root bn. This is one vector. The other vector is a1 by root b1, a2 by root b2, and this is the other n-dimensional vector. If you apply Cauchy on these two vectors, you should get this result, right? Now let's try to apply this inequality in questions. So the first one that we look at is this one. Let A, B, C belong to real positive and A plus B plus C is equal to 3. We have to prove that root over B by A square plus 3 plus root over C by B square plus 3 plus root over A by C square plus 3 is less than equal to 3 by 2 fourth root of 1 by ABC. Okay. So here, let's think of two vectors here. My u vector will be 1 by root over A square plus 3, 1 by root over B square plus 3, and 1 by root over C square plus 3. And my v vector will be root B, root C, root A. So applying Cauchy, I can say that u dot v whole square will be less than equal to mod u square into mod v square, right? So u dot v would give me root b by root over a square plus 3 plus, so this will become root b by root over a square plus 3 plus root c by root over b square plus 3 plus root a by root over a square plus c square plus 3 whole square. This is the LHS is less than equal to, when you do the mod u square and all will become 1 by a square plus 3 plus 1 by b square plus 3 plus 1 by c square plus 3 multiplied by b plus c plus a, right? Now b plus c plus a is actually equal to 3. So this is equal to 3 times 1 by a square plus 3 plus 1 by b square plus 3 plus 1 by c square plus 3, right? So great. We have this inequality right now. The square of what we need in the LHS is less than equal to 3 times this, right? Okay. So let's just write it on the next screen and we'll continue from this point. So we have root b by root a square plus 3 plus root c by root b square plus 3 plus root a by root c square plus 3 whole square is less than equal to 3 times 1 by a square plus 3 plus 1 by b square plus 3 plus 1 by c square plus 3. This is what we have here by direct application of Cauchy. And now we will say that a square plus 3 is actually equal to a square plus 1 plus 1 plus 1. So that should be greater than equal to 4 times 4th root of a square into 1 into 1 into 1. This is AMGM inequality. So that implies that a square plus 3 is greater than equal to 4 root a, right? We get this. So therefore, 3 by a square plus 3, or actually I can take the 3 outside. The RHS here is 3 times 1 by a square plus 3 plus 1 by b square plus 3 plus 1 by c square plus 3. And now it is coming as less than equal to 3 by 4 1 by root a plus 1 by root b plus 1 by root c. Why? Because from here we can say that 1 by a square plus 3 is less than equal to 1 by 4 root a. And similarly for the other terms also. So we have just reused that here, right? Now 1 by root a plus 1 by root b plus 1 by root c is equal to root over AB plus root over BC plus root over CA by root over ABC, and that can be written as less than equal to, I will apply AMGM on this term, root AB. I know root AB is less than equal to A plus B by 2 plus root BC is less than equal to B plus C by 2 plus C plus A by 2. And the whole thing is divided by root ABC, right? So the top part, actually, you will realize that that is equal to A plus B plus C by root ABC. So A plus B plus C has been given in the question, that is 3 by root ABC. So we know that this term is less than equal to this 3 by root ABC. So we can write that here, less than equal to 3 by 4 to 3 by root over ABC, right? So finally, we are getting this 3 will cancel. Actually, it will not cancel because this was already present here. So we have the square of our LHS is less than equal to 9 by 4 root ABC, right? So the LHS, which is simply this without the square, that is this, will be less than equal to, we will take the square root of this, so that will become 3 by 2 and 4th root of ABC, because here it was already a square root, so it will become a 4th root of ABC. So that proves our inequality, right? So notice that we have used Cauchy's in the beginning for vectors u and v, and after that we are using just AMGM multiple places, right? And that happens here, and we are able to prove it. Let's move on to the next question. Question 2 is this one. Suppose x, y, and z are positive numbers, and x plus y plus z is greater than equal to 3. We have to prove that 1 by x plus y plus z square plus 1 by y plus z plus x square plus 1 by z plus x plus y square is greater than equal to, is less than equal to 1. We have to prove this one. So we have to figure out some way to get a term like x plus y plus z square here, right? Okay. So we'll have to use Cauchy inequality somewhere. So let's try this case. Let's think of what we can say if x plus y plus z square multiplied by x plus y plus 1. If we think of these series of numbers, here we can say that the vector u vector is root x, root y, and z, and v vector is root x, root y, and 1. And then this term is basically mod u square multiplied by this term is mod v square. So that should be greater than equal to u dot v whole square by Cauchy. So what is u dot v here? U dot v, if you see here, is x plus y plus z whole square, right? So we are getting this should be greater than equal to x plus y plus z whole square. And from there, what can we say? We want to get a 1 by this term, right? We want this in the denominator. So we will get basically x plus y plus z square is greater than equal to x plus y plus z whole square by x plus y plus 1. And we can take the reciprocal, and by reciprocals we'll get 1 by x plus y plus z square is less than equal to x plus y plus 1 by x plus y plus z whole square, right? We are getting this. So basically our inequality, we can say 1 by x plus y plus z square plus 1 by y plus z plus x square plus 1 by z plus x plus y square will be less than equal to x plus y plus 1 by x plus y plus z whole square plus the next one will be y plus z plus 1 by x plus y plus z whole square. And lastly, it will be z plus x plus 1 by x plus y plus z whole square. Because we have established this case, right? So we are using it in all of these places, all of these places. So now if we prove that this quantity is less than equal to 1, then we are done, right? So let's try to prove this, because this is simpler because the denominators are common in this, right? So let's simplify it on the next screen. So we'll get basically, when you add it up, you will get 2 times x plus y plus z plus 3 by x plus y plus z whole square. And we should try to prove that this is less than equal to 1, right? Now, this is easy to check. How? We'll bring it on this side. We'll make it a quadratic. So x plus y plus z whole square minus 2 times x plus y plus z minus 3 is greater than equal to 0. We have to confirm whether this is true or not. If this is true, then this is true. And if this is true, our inequality is proved from the previous screen, right? So to confirm this, we can simply factorize it. Factorizing it gives us x plus y plus z plus 1 multiplied by x plus y plus z minus 3 is greater than equal to 0. Now in the problem itself, they have said that x plus y plus z is greater than equal to 3, which means that both of these factors are greater than 0, which means that this is true, and that implies that this is true. And if this is true, our inequality is true, right? So basically a simple application of Cauchy, but you have to be very inventive when you're building up that first inequality. So how do I handle the term x plus y plus z square? I used another vector x plus y plus 1 and used u and v vectors that as root x, root y, z and root x, root y, 1. That helps us to make the inequality into something easier because it became a homogeneous term after that when we applied Cauchy, right? Let's move on to the next problem. Question number 3. Let ABC be the lengths of the sides of a triangle. Lengths of the sides of a triangle. We have to prove that C plus A minus B whole power 4 by A into A plus B minus C plus A plus B minus C whole power 4 by B into B plus C minus A plus B plus C minus A whole power 4 by C into C plus A minus B is greater than equal to AB plus BC plus CA. So in this problem, many times you will realize that in triangles, when you have ABC as the length of the sides, there is a common substitution. It's called the tangent length substitution, where we can say x is equal to C plus A minus B, y is equal to A plus B minus C, and z is equal to B plus C minus A. if you use this, basically in a triangle, these are, if you draw the in circle, these lengths are being represented here, because you can say here that a plus b plus c is equal to x plus y plus z, right? From here, we can deduce that a plus b plus c is x plus y plus z. So what this does for us is x plus y by 2, a becomes x plus y by 2, b becomes y plus z by 2, and c becomes z plus x by 2. So if this length was called x and x and y and y and z and z, a is x plus z. So it's possibly not the in circle tangent length, it's probably the x circle tangent length. But that is not the focus right now. We are going to do this substitution because it helps us simplify the problem. C plus a minus b and all we'll substitute as x, y, and z. So the LHS here becomes basically x power 4 by a is x plus y by 2 and a plus b minus c is y, right? So this is 2x power 4 by y into x plus y. And similarly, there are three other terms, right? Okay. Correct. So let's write the inequality in terms of x, y, and z now. It is 2x power 4 by x plus y into y plus 2y power 4 by y plus z into z plus 2z power 4 is equal to x by x into z plus x. This is S. This is the LHS of the initial inequality. We have written it like this. So therefore, S by 2 is becoming x power 4 by x plus 5y plus y power 4 by y plus z plus z power 4 by z plus x into x. Right? Now, what we can say here is we multiply s by 2 with a new vector y into x plus y plus z into x plus z, z into y plus z, not x plus z, because I want to cancel the denominators, right? Z into y plus z plus x into x plus z. I want to multiply s by 2 and this, and I will consider this as a u vector. U vector will be x square by root y root x plus y, comma y square by root z into root y plus z, and z square by root x into root x plus z. And this will become my v vectors terms. V vector would be root y root x plus y, root z root x plus z, y plus z, and root x multiplied by root x plus z. So if you think of u vector like this and v vector like this term here is simply mod u square. So it is mod u square into mod v square. That is the product of s by 2 into this should be greater than equal to u dot v whole square, right? So what is u dot v whole square? When you do dot product here, you will realize that it is x square plus y square plus z square whole square, right? So what we are getting is this expression s by 2 multiplied by y into x plus y plus z into y plus z plus x into x plus z is greater than equal to x square plus y square plus z square whole square, right? So what we get from here is S is greater than equal to twice of x square plus y square plus z square whole square divided by y into x plus y plus z into y plus z plus x into z plus x, which is equal to twice of x square plus y square plus z square by, if you simplify this a little bit, it becomes x square plus y square plus z square plus xy plus yz plus zx, right? Now, this can be written as, we know that x square plus y square plus z square is greater than equal to xy plus yz plus zx. We know this. So the denominator here, we can make the denominator larger by replacing this as x square plus y square plus z square, right? So if the denominator is made larger, we can say that s will be greater than equal to twice of x square plus y square plus z square by x square plus y square plus z square plus x square plus y square plus z square, right? Because when you replace the denominator with a larger term, this quantity is lesser than this. And we already had s greater than this. So s must be greater than this, which is equal to 1. So basically, no, here there was a square, which is not equal to 1. It is equal to simply x square. The 2 gets cancelled here. X square plus y square plus z square also gets cancelled. And you are left with simply x square plus y square plus z square. So you are getting finally this. S is greater than equal to x square plus y square plus z square. And now we can use the fact that this is greater than equal to okay, we'll do it on the next screen. So far what we have gotten is S is greater than equal to x square plus y square plus z square. So we can actually prove that x square plus y square plus z square is greater than equal to x plus y plus z whole square by 3. How? Think about it. Root over x square plus y square plus z square by 3 is the QM. It is the square mean, right? Square mean of x square, y square, z square. So that should be a square mean of x, y, z. So that should be greater than the AM, right? X plus y plus z by 3. So that implies that x square plus y square plus z square by 3 is greater than equal to x plus y plus z whole square by 9. So 3 gets cancelled. So we are getting this, right? So this is a consequence of QM is greater than AM. Square mean is greater than equal to arithmetic mean. So we can write it here like this, right? And now x plus y plus z was equal to ABC. So we are getting S is greater than equal to A plus B plus C whole square by 3. And that is greater than equal to AB plus BC plus CA. This is greater than equal to AB plus BC plus CA is obvious because when you do A plus B plus C whole square minus 3 times AB plus BC plus CA, you end up with A square plus B square plus C square minus AB minus BC minus CA, which is greater than 0 always, right? So therefore, this quantity by 3 should be greater than equal to AB plus BC plus CA. And we have proved our original inequality. S stood for the LHS, right? So we have shown that LHS is greater than AB plus BC plus CA. So notice what ideas we have used. We used Cauchy, we choose first of all a tangent length substitution. We just simplified the problem by substituting x as c plus a minus b, y as a plus b minus c, and so on. Then we used Cauchy's inequality. We called the entire LHS as S, and we multiplied it with y into x plus y plus z into y plus z, and so on. After Cauchy, we used QM greater than equal to AM here, right? And finally, at the end, we get the proof, right? Okay. In the next one, next problem is this one. Question number 4. We are given n greater than equal to 2 positive reals numbers a1, a2 till an that satisfy the inequality summation I goes from 1 to n ai multiplied by summation 1 by ai I goes from 1 to n is less than equal to n plus half whole square. We have to prove that maximum of a1, a2 till an is less than equal to 4 times minimum of a1, a2, an. So the maximum and minimum values of this sequence of positive reals, we have to prove that this is the inequality they satisfy. So let's call the minimum value as small m and the maximum as capital M. We have to show that capital M is less than equal to 4 small m. This is what we need to prove. Now what is given to us? We are given that n plus half whole square is greater than equal to a1 plus a2 plus an multiplied by 1 by a1 plus 1 by a2 plus 1 by an, right? So this can be written as this is equal to m plus a2 plus a n minus 1 plus capital M multiplied by 1 by m plus 1 by a2 plus 1 by capital M. What have I done here? I have assumed without loss of generality that a1 is less than equal to a2 less than equal to an. An becomes our greatest term and a1 becomes our least term. So if the numbers are not properly ordered, you can relabel the numbers, right? You can relabel the numbers so that they are in ascending order. This is not assuming anything new. We just relabel the numbers, and we get, let's assume for now that a1 is the smallest element, so that is m, and an is capital M. So I have now just written this sequence of numbers, the addition, as m plus this stuff and plus capital M, and here 1 by m till 1 by capital M, right? Now if I apply Cauchy-Schwarz here, this will be greater than equal to, consider this as the mod u square and this as the mod v square. So it should be greater than equal to u dot v whole square, right? And when you do u dot v whole square, you will get basically, okay, before that I will do one step. I will just write it here. We have n plus half whole square is greater than equal to, I can rewrite it as m plus a2 plus a3 till capital M. And here I can start with a 1 by capital M and then write 1 by a2, 1 by a3, and so on till 1 by m, right? So I get 1 by an minus 1 here, 1 by an minus 1 here, right? I've just exchanged the terms here, 1 by m first and 1 by small m later, right? And now I'll apply Cauchy using this as the mod u square and this as the mod v square. So it will be greater than u dot v square, right? So it will be greater than root over m by m plus 1 plus 1 root over m by m whole square, right? Why are you getting 1 and all? Because when you do dot product, the vector components were root m, root a2, root a3 till root capital M, and this side the components were 1 by root M, 1 by root A2, 1 by root A3 till 1 by root small m. So when you do dot product, these terms will multiply and become 1 each, right? Correct. So this is equal to root over small m by capital M plus root over capital M by small m plus the n minus 2 terms, n minus 2 whole square, right? Now we have this inequality, n plus half whole square is greater than equal to this. So taking the square root, we can say that n plus half is greater than equal to basically root small m by capital M plus root capital M by small m plus n minus 2. So from here, n gets cancelled and we get root small m by capital M plus root capital M by small m is greater than equal to basically not greater than equal to, it's less than equal to 5 by 2, because this is coming less than equal to 2 plus half, which is 5 by 2. If you simplify this expression, basically simplify it like this: m plus m by root is less than equal to 5 by 2, and take it on, bring everything on one side, you will get 2 capital M minus 5 root plus 2 small m is less than equal to 0. Factorizing this, you will get 2 root m minus root small m multiplied by root m minus 2 root m is less than equal to 0. And for this term to be less than equal to 0 by wavy curve method, the value of root m should be between, these are the values at which the expression is vanishing. So in between the values are negative, right? Above this it is positive and positive. So for this inequality to be true, root m should be less than 2 root small m. So that becomes m is less than 4m. So we have proved the statement that we intended to start with, right? That was the question. Let's go on to the next one. Question number 5. Here, let A1, A2 till AN be given real numbers, not all of which are 0. Not all of which are 0. And let R1, R2, Rn be real numbers. If an inequality summation k goes from 1 to n, rk xk minus ak is less than equal to summation k goes from 1 to n xk square whole to the power half minus summation k goes from 1 to n ak square whole to the power half is satisfied. This inequality is satisfied for any real numbers x1, x2 till xn. For any choice of real numbers x1 to xn, this inequality is always true. We have to find the values of r1, r2 till rn. So in this question, it is slightly different. We are given an inequality that is true for all possible values of xl, right? So let's use the inequality in different cases. The first thing we will do is let x1, x2 till xn be all 0. Because it was satisfied for all real numbers, we have the left hand side becomes summation k is equal to 1 to n minus rk ak is less than equal to, this one will vanish and you will have minus summation k goes from 1 to n ak square to the power half, right? So when you multiply by minus 1 here, you will get summation k is equal to 1 to n rk ak is greater than equal to summation k is equal to 1 to n ak square to the power half. So this is the first condition that we are getting, right? So keep that condition in mind. We'll use it later. The second one, the second condition is if we choose each of the xk to be equal to twice of ak, right? For k goes from 1 to n. In this case, the inequality tells us summation k is equal to 1 to n rk times ak is less than equal to summation of k is equal to 1 to n. This is twice of ak, so it's 4 ak square and whole to the power half minus summation k goes from 1 to n ak square to the power half. So the 4 comes out, becomes a 2. So this is equal to 2 ak square summation minus 1 ak square summation. So that is simply ak square summation k goes from 1 to n to the power half, right? So we are getting from here that summation of rk ak is less than equal to this, right? Okay. So from 1 and 2, 1 and 2. Remember the first condition, we are getting summation rk ak is greater than equal to summation ak square power half. Now we are getting it is less than equal to. So that implies actually summation rk ak must be equal to summation ak square power half, because you are getting less than equal to also and greater than equal to also. But once we establish this, we can write Cauchy for this, right? We can say summation of rk ak must be less than equal to summation of rk square power half multiplied by summation ak square power half, right? Must be less than equal to. And now, because this is equal to summation ak square power half is less than equal to this is coming, we are using this condition here in the LHS. We can see from here that summation rk square power half is greater than equal to 1, right? This is coming from here using everything that we have done before. Great. Now we go back to the original inequality and we choose xk to be equal to rk for k is equal to 1 to n. In this case, the original inequality gives us summation k goes from 1 to n rk square minus rk ak is less than equal to summation of rk square power half minus summation of ak square power half, right? Now we'll split this one into two separate terms, summation rk square minus summation rk ak less than equal to summation rk square power half minus summation ak square power half. And now we know that this quantity is equal to this quantity, right? We have already shown this before. The summation of rk ak is equal to ak square power half, right? Right. So we can remove that from the inequality and we are getting summation of rk square is less than equal to summation of rk square power half, which basically implies that summation of rk square is less than equal to 1, right? This is like saying x is less than equal to root x. That implies x is less than 1, right? So now notice this, we have gotten summation of rk square is less than 1. And in the previous case, we had concluded that summation of rk square in the previous case was coming greater than equal to 1. So together with this, it means that we have summation of k goes from 1 to n rk square is equal to 1, right? Great. And earlier we had also shown that summation of k goes from 1 to n rk ak was equal to summation of ak square k goes from 1 to n power half, right? So now this implies that we can write it as, since this is equal to 1, we can multiply a summation of k is equal to 1 to n rk square power half here, right? Because this is 1, we can use square root of that and multiply it here. Now we are getting a different situation. We are getting Cauchy on this, but it is the equality case of Cauchy's inequality, right? So Cauchy's inequality, you should usually say what? You should usually say summation of rk ak is less than equal to summation of ak square power half summation of rk square power half. But in this case, we are getting summation of rk ak is equal to summation of ak square power half and summation of rk square power half. So the equality case in Cauchy's inequality comes only when the two vectors are proportional, right? So there must be a lambda such that rk is equal to lambda ak for all k goes from 1 to n, right? Great. So if that is the case, now we can use the fact here, because we know that summation rk ak is equal to summation of ak square power half, and now we can say rk, this implies rk is lambda ak, so it is lambda ak square is equal to summation ak square power half. So lambda comes outside, this is summation ak square is equal to summation ak square power half, which implies that lambda is equal to summation of ak square power minus half, right? So basically, what this tells us that each of the r's, rj must be equal to aj by summation of k goes from 1 to n ak square power half, right? And j can vary from 1 to till n. If you use any rj that is satisfied, that satisfies this relation, we will ensure that the inequality is always true. The inequality mentioned in the problem is always true. So notice we have used many different situations here. We have used Cauchy's inequality several times, and also used the condition when Cauchy's inequality becomes an equality. Now we will look at the last problem here. This is question 6. Suppose x1 to xn are n greater than equal to 2 positive numbers, and summation of I goes from 1 to n xi is equal to 1, right? We have to prove that summation I goes from 1 to n xi by root over 1 minus xi is greater than equal to 1 by root over n minus 1 summation of I goes from 1 to n root xi. This is what we have to prove. Now think about it. What is xi by root over 1 minus xi? That can be written as 1 by root over 1 minus xi minus root over 1 minus xi. If you simplify this, it will come as the same thing. So therefore, summation of xi by root over 1 minus xi can be split as two separate summations. This is the first summation is this minus summation of root over 1 minus xi, right? So for positive numbers, for positive yi, we know from the corollaries of our AMGM that we have established in the beginning of the video, summation of yi into summation of 1 by yi is greater than equal to n square. We had seen that earlier. So from there, we can say that summation of 1 by yi is greater than equal to n square by summation of yi, right? So therefore, now we'll choose yi is equal to 1 minus root xi. We are choosing yi here. And from here, we can say that summation of 1 by root over 1 minus xi is greater than equal to n square by summation of root over 1 minus xi, right? We have this. Now, we will work with the Cauchy inequality. And we'll say summation of I goes from 1 to n root 1 minus xi is less than equal to summation of I goes from 1 to n 1 whole to the power half, and summation of I goes from 1 to n 1 minus xi whole to the power half. What are we doing here? We are using u dot v and mod u mod v, where u is what vector? U is the vector with components 1 minus x1 root over 1 minus x2 and so on, root over 1 minus xn, and v is the vector with components 1, 1 and so on. So u dot v will give me the left hand side, and mod u and mod v will give me this, right? Correct. So this is direct Cauchy's inequality. So we get from here summation of I goes from 1 to n root over 1 minus xi is less than equal to, this becomes a n, so it is root n, and this part becomes 1 minus xi summation will become n minus x1 plus x2 till xn, and in the problem we have seen that x1 plus x2 plus xn is equal to 1, so this is root over n minus 1, right? So we are getting these two results. The first result is this, and the second result is this, which we got by Cauchy, right? The third result that we can establish is this result. Summation of I goes from 1 to n root xi is less than equal to root n. How? We'll do again a dot b is less than equal to mod a mod b. Here a vector will again be root x1, root x2 and so on till root xn, while b vector will be 1, 1 and so on. So mod a would be what? Root over x1 plus x2 plus xn, and this will be root of n, right? But x1 plus x2 plus xn is equal to 1, so it is simply less than equal to root n, right? This inequality is true. So this is the third result that we have. So now what we needed to prove was summation of I goes from 1 to n xi by root over 1 minus xi, which we have split into two different summations. Summation I goes from 1 to n 1 by root over 1 minus xi minus summation of I goes from 1 to n root over 1 minus xi. And now we will say that this should be greater than equal to, the first result was claiming that this one will be greater than equal to n square by summation I goes from 1 to n root over 1 minus xi minus summation I goes from 1 to n root over 1 minus xi here. So we already know that this stuff was less than root over n into n minus 1. So it will be greater than equal to n square by root over n into n minus 1 minus root over n into n minus 1, right? Because when you are subtracting, you can subtract a bigger quantity here, right? So you are subtracting a bigger quantity here and you are dividing by a bigger quantity also. That makes this smaller, right? So if you simplify this, what you will get is, I will say thus this part will be equal to n square minus n into n minus 1 by root of n minus 1. This becomes n by root over n into n minus 1, right? So this becomes equal to root over n by n minus 1, which is equal to, basically we have said LHS is here, that is greater than equal to this, right? So I'll just use that. So I'll say summation 1 by root over 1 minus xi minus summation root over 1 minus xi is greater than equal to, I have established, root over n by n minus 1. And we have already seen earlier in point 3 that summation of xi, root xi, is less than equal to root n, right? So we can say that this is greater than equal to root xi summation I goes from 1 to n divided by root over n minus 1, right? So we are able to now establish that summation 1 by root over 1 minus xi minus summation root over 1 minus xi is greater than equal to 1 by root n minus 1 summation root xi. So we are using Cauchy-Schwarz in multiple places. You have to go back to point number 1 and point number 2 if you are not very sure. But ultimately, 3 times we have used Cauchy-Schwarz here, and we are able to prove the condition, right? So that is that, and that's about it for this inequality. We have seen several ways in which it is applied. Hopefully, you should be able to take what you learned from this video and apply it to problems. So that's it for now. The next inequality that we'll be discussing is the rearrangement inequality. So we'll see that in the next video.